Hi, today we're going to look at finding the probability of a compound event. What is a compound event? Well, a compound event consists of two or more single events. For example, the birth of a child is a single event. The birth of four children make up a compound event. Or, more likely, flipping a coin and rolling a die. What's the probability of getting heads on the coin and getting a 6 when we roll the die? That is a compound event. So to do that, we need to know the number of outcomes. And one thing that we can do is find what we call the sample space. All of those possibilities is called the sample space. So in this example, you randomly choose a crust and a style of pizza. Find the sample space. How many different pizzas are possible? So we have a choice over here on the left of thin crust or stuffed crust. And then we have styles Hawaiian, Mexican, pepperoni, and veggie. The easiest way to list out the sample space or all of the possibilities is to make a tree diagram. So I've made one here, and I'm just going to slide this over. So here we have crust. So we have thin and we have stuffed. We have two choices for crust. Off of that branches, we have four different styles of pizza. So I could have a thin crust pizza that is Hawaiian style, Mexican, pepperoni, veggie, or I could have a stuffed crust pizza that's also Hawaiian, Mexican, pepperoni, or veggie. So that gives us a bunch of different possibilities for pizza. And that list of possibilities I get from this tree diagram, but I list them out. So I list them out like this. So here are all the outcomes. Thin crust Hawaiian, thin crust Mexican, thin crust pepperoni, thin crust veggie, and so on all through the stuffed crust. So I have a list here of 8 different combinations. This list of outcomes is the sample space. So another thing that's important here is the fundamental counting principle, and we're going to get to this after we do this first example here. An event has so many possible outcomes, and the easiest way to do that is to multiply the number of outcomes of one event times the number of outcomes of the second event. So suppose you have 4 shirts and 2 pairs of pants. How many different outfits can you make? Well, we have 4 shirts, 2 pairs of pants. 4 times 2 gives us 8 outcomes. Sometimes we just need that number to list that number on the bottom when we do probability as our total number of outcomes. So finding sample space. This is on your PDF if you're following along with the PDF. So finding sample space. So what I want to do to find this is I want to list all of the possible outcomes. So at a sub shop, Gigi can choose ham, turkey, roast beef on either white or wheat bread. So I have 2 choices of bread. So I have white and I have wheat. And off of that, I have 3 different choices. So I could have white ham, I could have white turkey, and I'm listing all of these because it says list the sample space, find the sample space. So the sample space is a list of all the different combinations, and I could have white roast beef. I'm going to abbreviate that RB. So I could also have ham on wheat. I could have wheat turkey. This is a list of the sample space. And I can have wheat roast beef. So a total of 1, 2, 3, 4, 5, 6 possible combinations. But this listing out of all of the combinations is the sample space. So when they say find the sample space, you have to list those out. If you need to make a tree diagram, make a tree diagram, but you still have to make the list once you make the tree diagram. All right, use sample space from above to find the following probabilities. Well, we know that there are 6 different outcomes. What is the probability that she chooses a ham sandwich on white? Well, if we look back at those combinations in the sample space, there is 1 out of 6 combinations that is a ham sandwich on white bread. What is the probability she chooses a turkey sandwich? So if I look back, how many turkey sandwiches were there? Well, here's a turkey and here's a turkey. So there are 2 turkey sandwiches out of 6. So I'm going to put 2 over 6. And then, of course, I want to simplify that into lowest terms, so 1 out of 3. What's the probability she chooses a sandwich on wheat bread? So there are 6 total combinations, but there were 3 of them, the ham, turkey, and roast beef, on wheat bread. So that's 3 out of the 6 possible combinations, or 1 out of 2. Those are your probabilities, and using sample space to find those. All right, let's look at example number 4. Cameron wants to buy a new laptop. He decided to build his own laptop. Find the total number of possible computers he can build given the features below. So he has hard drive choices, he has style, and then he has color. So I can list all this out, all the sample spaces, or I can use the fundamental counting principle and multiply the possibilities of each one. So he has 3 possibilities for a hard drive, 2 for style, and he has 1, 2, 3, 4, 5, 6, 7 right there for color. So fundamental counting principle says I can multiply the number of outcomes times the number of outcomes, and in this case, 3 times 2 times 7. So when I do that, 3 times 2 is 6. 6 times 7, that's a 7, equals 42. How many possible outcomes does he have? He has 42. Without making a tree diagram, without listing out all of the possibilities, I just multiply using the fundamental counting principle, because this would be a pretty big tree diagram if I had to make one there. I could, but it's a lot easier. Number of outcomes times number of outcomes times number of outcomes gives you the total number of possibilities. All right, you spin the spinner and flip a fair coin. Find the probabilities of the events. So I can list out the sample space. My sample space would be if I make a heads on the coin or tails on the coin, and then off of that, I'm going to flare out all the possible outcomes for the spinner. There's 5 things on the spinner, and I could do this here as well for the tails. 1, 2, 3, 4, 5. So spinning a 2 and flipping tails. So here's tails, 2. There are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There are 10 outcomes. I can see that over here from my tree diagram. And on tails, there's only one way to get a 2. So 2 out of 10. No, not 2 out of 10. Oh, one way of getting a 2 out of 10. So it's 1 out of 10. 1 out of 10. Spinning a 7, and flipping tails. Well, there's no 7s at all, so it's 0 out of 10. 0 out of 10, which equals 0. Not spinning a 4 and flipping tails. Well, here's tails. How many are not 4s? Tails 1, tails 2, tails 3, tails 5. So there are 4 ways to get a number that's not 4 out of 10 possible outcomes here. Total outcomes here is 10. So 4 out of 10. And that simplifies again. We want to simplify any of those probabilities to lowest terms. So 2 out of 5. All right, so if I was to ask you all of the different combinations that you could use on this lock, we would have to make a pretty big tree diagram. So in this 3-wheel lock, the numbers are 0 to 9. Now 0 counts as a number, so 0 to 9, there are 10 different outcomes for that first wheel, 10 different outcomes for the second wheel, and 10 different outcomes for the third wheel. This would make a big tree diagram. But again, our fundamental counting principle says we're going to multiply 10 outcomes for the first wheel times 10 outcomes for the second wheel times 10 outcomes for the third wheel. This gives me 10 times 10 times 10. There are 1,000 different combinations on that lock. Now, to be more secure, like the locks we have on our lockers or locks you use on a padlock here, you have 0 through 39. So Here we would multiply 40, 0 through 39, that's 40 different digits, times 40 times 40. And you can see that there's a larger number of combinations there. Also, when we pick security passwords, there's a ton of combinations there. And when they make you make a capital letter and a number, the number of combinations goes up tremendously. All right, so back to the notes here. Probability of an independent event. An independent event, one event has no effect on the other. So a compound event could be spinning a spinner and flipping a coin. Spinning a spinner, it doesn't matter what the outcome is. When I flip that coin, I still have two outcomes available there. Neither one of those affected each other. Those are independent events. And what we do is we multiply the probability of one event times the probability of the second event. And we're going to show you that. Now, dependent events, the number of outcomes changes because of the first event. So if I was picking letters from a bag and I held onto the letter, there was originally 10. The second time I reach into that bag, there's only 9 letters in there. So that does affect the outcomes of the second event. So those are dependent, and we're going to look at those. All right, so here's an independent event. Here's a spinner, here's a coin. You spin the spinner and flip the coin. What is the probability of spinning an odd number and flipping tails? So odd numbers on this, there are 3 out of 5. So the probability of getting a 3 out of an odd number on that spinner is 3 out of 5. I write that down. The probability of getting tails is 1 out of 2. There's 2 sides, one of them's tails. There's the probability of each event separately. Now I'm going to multiply these. Remember, multiplying fractions or ratios, numerator times numerator, that gives me 3. Denominator times denominator, that gives me 10. That's all there is to this. These are independent events because the spinner had no effect on the number of outcomes on my second event. I still had 2 outcomes on that coin. It had no effect. All right, dependent events. So let's look at this event. You have a bag of marbles. 5 are pink, 7 are yellow, 3 blue, 4 black, and 1 red. Suppose you pick 2 marbles. What is the probability choosing a pink marble? All right, so we have 5, 7, 3, 4, 1. So that is 10, 20 marbles. Out of 20 marbles, how many of them are pink? 5 of them are pink. So when I first reach in that bag, there are 5 out of the 20 that are pink. So I hold on to the first marble that I pick. So when I reach in again, as if I'm reaching in again, and it doesn't matter if you pick them both at once, it's still the same thing. There is no longer 20 marbles in there. There's 19 marbles in there and 1 less pink marble. This is what I have now. What is the probability of doing that? I have 20 on top, and 20 times 19 is 380. That's the probability. Now I can simplify that. It becomes 2. I can divide both by 10. 2 out of 38, and that simplifies down to 1 out of 19. There's your probability for that. But these are dependent events because the number of outcomes changed because of the first event. Picking the first marble changed the number of outcomes. I no longer have 20 marbles in there. I only have 19. So know the difference between independent and dependent events. The number of outcomes changes because of the first event. It is a dependent event. But whether it's dependent or independent, number of probability of the first event times the probability of the second event gives you the total probability for this compound event because we're doing more than one thing. All right, let's look at number 3. You are randomly chosen to be a game show contestant, or people are randomly chosen to be game show contestants from an audience of 100 people. You are with 5 of your relatives and 6 other friends. What is the probability that one of your relatives is chosen first and then one of your friends is chosen second? So out of 100 contests, So your relatives, how many relatives are there? You have 5 relatives out of the 100. So the probability of one of your relatives being chosen is 5 out of 100. Times the probability of one of your friends being chosen. Well, 5 is relatives. So you still have 6 friends there. But there are no longer 100 people in the audience because somebody has been chosen for that first one. So now we have 99 here. All right, and I can multiply this or I can simplify this, and I'm going to simplify it because it's easier. 100 and 5 are both divisible by 5, so this is 1, this is 20. 6 is divisible by 3. Oops, divisible by 3. 6 divided by 3 is 2. So all I'm doing is simplifying these ratios. So this is 2 divided by 3. This is 33. When I multiply this, oh, and I still now have a 2 here and I have a 20 here. I can divide that. 10 and 1. So this equals 1 out of 330. That is your probability, 1 out of 330. 10 times 33. All right, let's look at number 4. You spin the spinner and flip a coin. So this is an independent event. The spinner is going to have no effect on the number of outcomes of the coin. Find the probability of the compound event. Spinning an odd number and flipping heads. So spinning an odd number, I have 1, 2, 3. 1, 3, and 5. 3 out of 5. Times, and you show this work, right? The probability of each one. And flipping heads is 1 out of 2. 1 out of 2. When I multiply that, this equals 3 out of 10. There is your probability. B, not spinning a 5. So there's 4 out of 5. And flipping tails, the probability of that is 1 out of 2. And again, show each probability that you're multiplying together. This gives me 4 out of 10, which is 2 out of 5 when you simplify it. Spinning a 2 and flipping heads. Well, how many ways are there to get a 2 out of the 5? It's only 1 out of 5 times flipping heads is 1 out of 2. So you get a 1 in 10 chance. That is your probability. That's compound probability of independent events. One event does not affect the number of outcomes of the second one. That's what makes that independent. All right, number 5, you randomly choose one of the tiles without replacing it. So that means the number of outcomes are going to change. So these are dependent events. So without replacing, you choose a second tile. Find the probability of the compound event. Choosing 2 odd numbers. All right, so we start off, there are 7 outcomes in there. There are 7 tiles, right? Here's the numbers, 1, 2, 3, 4, 5, 6, 7. Choosing an odd number. So we have 1, 2, 3, 4. So 4 out of 7. When you reach in again, there's no longer 7 tiles there. There's only 6. And we subtract 1 because we would have chosen 1 the first time. And that's 3 out of 6. When you multiply those, you could simplify before multiplying, but I'm just going to multiply and gives me 12 out to 42. 7 times 6 is 42. And I can simplify that. Both of those are divisible by 6. And that gives me 2 out of 7. There's your probability. 2 out of 7. Right? Did I multiply that right? Divide by 6, divide by 6, 2 out of 7. Choosing a 4 and then a 7. So how many 4s are there out of 7 outcomes? Choosing a 4, there's one way to do that out of 7. When I reach in again, there's only 6 numbers left in there. And how many even numbers? Now I chose a 4 the first time, so I'm going to eliminate that. So the 6 numbers that are left, I have 1, 2 even numbers left. So it's 2 out of 6. Multiply that. That's 2 out of 42. Or 1 out of 21. Remember, these are dependent events because the number of outcomes are changing after my first event. My first event is choosing that first one. All right, choosing a 6 and then a prime number. All right, choosing a 6, there's only one way out of 7 to do that. Prime number are numbers that are only divisible by 1 and themselves. 1 is not a prime number. So 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is a prime number here. So that's 1 out of 7 to begin with. Oops, it keeps writing a tail on my number there. So we start off with getting a 6, probability is 1 out of 7. Probability of getting a prime number, there are 6 numbers left. 2, 3, 5, and 7, so that's 4. When I do that, that's 4 out of 42. We can simplify that to 2 out of 21. And one last one there, you randomly pull 2 bills from your wallet. What is the probability? They are both 20. So how many bills are there? I see 1, 2, 3, 4, 5, 6. So out of 6, first bill that you pull out, how many 20s are there? It looks like there's 2. 2 out of 6 times, well, you took the first bill, so there's no longer 6 there. There's 5 there. And there's no longer 2 20s. It's 1 out of 5. Multiply that, you get 2 out of 30. And simplify that, that's 1 out of 15. This would be dependent events. All right, there you have it. Dependent, independent events, probability of compound events. Compound events because we're doing more than one thing. We're pulling more than one tile. We're flipping a coin and spinning a spinner. So that's what makes it a compound event. Dependent events, the number of outcomes changes because of the first event. Independent, the outcomes do not change because of the first event.